So if we know the derivative of the objective function j with respect to the outcome of an operation, how do we compute the derivative to the inputs of that operation? Chain rule, yes. So the assumption here is that every operation is an analytic operation. Every operation has, it's simple enough so that the derivative of the output of that operation to all of its inputs have a simple expression that can be evaluated very easily. Well, maybe the derivative of the final output to the inputs of the chain of operations can be very complex, can be many pages long if you actually derive it using Mathematica. But for every single element in that huge chain of operations, the partial derivatives of that operation only should be very simple. So if we know the derivative of j with respect to the outcome of a simple operation, the derivative of the same j to the inputs of this simulation should be of that small operation should be very easy to compute, right? So for example, this one would be equal to dj times dj dun, and this is dj which is 1 times dj ds. I mean, here it's pretty obvious. Okay, now backpropagation means I go backwards through the chain of calculations. What is the second last operation to be computed? It's the calculation of un, right? So we already know the derivative of j with respect to the outcome of that second last operation, right? Because it's part of the inputs to the very last operation. So then we follow the same rule that we already know the derivative of j to the outcome of this operation. We try to get the derivative of the same j to the inputs of that second last operation. What are the inputs? un minus 1 and s, right? Okay. So here, we propagate it from this node backwards. So the red is kind of the backpropagation. Now we propagate to here. So here, what we compute is partial j, partial un minus 1, and partial j, partial s. And again, this is assuming s to be constant throughout, s to be constant in the evaluation of this operation, right? And dj ds is assuming un minus 1 now being constant. So how do we do that? This is dj ds is actually the summation of two parts. Now the chain rule, the application of the chain rule is a little bit more complex. The first part is from here. This is dj ds assuming assuming un is constant, and plus the new contribution dj dun times dun ds, where dun ds is the partial derivative of the second last operation. And here again, dj dun is dj dun minus 1 is dj dun times dun minus 1. And again, this is the partial derivative of the second last operation. Does it make sense? Okay, so this just keeps going forward, going backwards and backwards throughout the chain of calculations. Finally, what we are going to be computing is partial j, partial u0 over here, right? And then partial j, partial s, assuming u0 is constant. This is done by accumulating all of these derivatives, assuming u1 is constant, plus partial j partial u1 times partial u1 partial s, right? Where this again is the summation of two components and the summation of two components. So this is basically accumulation of all such terms backwards from un all the way to u1. Okay, the final step is propagate through the very first operation, which is the calculation of u0. Okay, so basically, finally, djds, right? This djds is basically, I no longer assuming anything else to be constant anymore, right? So after I propagate it all the way through u0, then I don't have to assume anything else to be zero, to be unchanged, is equal to partial j partial s, assuming u0 is 0, plus partial j partial u0 times du0 ds, because u0 is only a function of s. And this is the very last partial derivative of a component in the calculation. So this is the procedure that computes djds. And what's the advantage of this? Is that this single procedure computes the derivative to all components of S at the same time. So what's the difference if S has multiple components, or if I'm doing this with respect to a different S? I don't have to change any of these djdus, right? All of these djdus actually doesn't depend on anything about what S is. The only difference is when I'm computing this, the very first seed of djds is different, and every time I accumulate something onto this djds, so basically every time I add this, that is different. The whole procedure actually doesn't depend on the most expensive part, which is accumulation, which is computation of the djdus. It doesn't depend on what S I have. It doesn't depend on how many S's I have. Right. So through this procedure, it's called backpropagation. We have computed djds. No matter what S is, and no matter how many S there is, we compute the gradient in one shot. All right. Any questions about this? So this is kind of explanation of this backpropagation algorithm, which many machine learning classes actually they skip the derivation and explanation of this algorithm, just to treat it as, oh, this is something you can just use in a package. All right, but it's actually very useful to know how this works, and you can use machine learning packages like TensorFlow, which does a lot of this for you. If you write all of these operations, like u equal to un, all of these operations in a symbolic form, which is what these machine learning packages take, then they can compute the partial derivatives for you, just like Mathematica computes the partial derivatives for you. And then they do this backwards multiplication for you, assuming each calculation involves massive amount of data. And it becomes less and less efficient if your calculation deviates from this typical usage of machine learning, which is for every step you have relatively small number of steps on the order of tens and hundreds, but each step involves massive amount of data. So if that's the case, use these packages for doing backpropagation is ideal. If not, if you have, for example, if you're solving an ordinary differential equation where each step contains a small amount of data, but you have thousands and millions of steps, it's usually not a very good idea to use these packages.